Hello lecturer and everyone, we are Rup UMA and today we present our work for assignment 1, classification. In this assignment, we study classification on 3 data type, text, image, and multimodal image text data. Our presentation has 5 parts: overview, text classification, image, multimodal classification, and then we'll conclusion. The first one is overview. There are 3 tasks. We will use 20 news group for text, diabetic retinopathy detection for image, and UBMC food 101 for multimodal. The goal of the assignment is not only to train model but also to build reprocessing pipeline, compare model families, and analyze results with table figures. So the first one is text. For the text start, we use 20 new group dataset will contain 20 classes. After reprocessing and splitting, we have 8,811 training sample and 2,203 validation samples and 7,317 test samples with an average length of about 186.74 words. So our main goal here is to compare RNN and transformer approach for multi-class text classification. So we move to the EDA. From EDA, we find out that the dataset is relatively balanced with a max to mean plus ratio of 1.64. So severe imbalance handling is not necessary. We also find that document length varies a lot. The median is 86 words, but the maximum reaches 11,765. So padding and truncation are necessary. For the steward, the average token length is 375.02, while max length is only 256. So around 24% of sample are truncated. So the next one is reprocessing input pipeline. Our reprocessing starts with cleaning and normalization, then removing empty or too short sample, and finally splitting into train, van, test set. After that, we build 2 different input pipelines. For by LSTM, we use word level tokenization, a vocabulary of about 41,600 words, and button token IDS with second length. For distributor, we use the regen tokenizer distributor by encase and relay input IDS and attention mask with a maximum length of 256. For the model, our main comparison is still by LSTM versus distributor. Because that they require RNN versus transformer comparison, we also include embedding mean pooling as a small neural baseline just to check whether a symbol learned. Embedding can already work before using a stronger sequence of model. Then on the transformer side, we extend the comparison with frozen backbone and LLRD study different fine-tuning strategy. The main result is that transformer model clearly outperformed the RNN model in our setup. By LSTM reached 34.30% accuracy, while distributor frozen already reached 62.73%. The best result come from distributor fine-tune with 72.23% accuracy and about 0.770 macros F1. LLRD is very close with 71.85% accuracy, but it still does not surpass full fine-tuning. And in this first attention, we compare 3 transformer training strategy: frozen, full fine-tune, and LLRD. The frozen model is much cheaper with a training time about 548 and 87 seconds, but its performance is much lower. Full fine-tuning gives the best result with the distributed LLRD is very close but slightly worse. So the takeaway is that raising safe cost, but updating the backbone gives the strongest performance. And for the efficiency, we also compare the efficiency of the distributed variant using trainable parameter latency, throughput, and big GPU memory. The interesting result is that inference cost is very similar across the 3 variants, with latency only around 10.67 to 11.18 milliseconds per sample. So the main trade-off here is not inference but training cost versus accuracy. And finally, we perform error analysis on the best test model with a distributed fine-tune. The most common mistake happen between semantically similar class, such as talk, point politics, point mix, and talk politics guns, or talk religion mix and short religion region. This shows that the model does not fail randomly. Instead, it mainly structured on class with overlapping vocabulary and cloud meaning. So for overall in the test session, we build 2 different input pipelines, compare RNN and transformer as right, and extend the study with fine-tune strategy, efficiency, and error analysis. Our final conclusion is that this to work with full fine-tuning in the strongest test model in our experiment.
For our image classification task, we chose diabetic retinopathy, which is the leading cause of blindness in the working age population. This disease affects over 40% of people with diabetes, can be slowed if DR is detected early. So you can see from the images that the retina with DR has very clear visual distinctions, having more bloodshot enlarged blood vessels and aneurysms. So the dataset that we chose, originally released for a 2015 CACL competition, serves as a benchmark for automated medical image analysis. The task is a 5-class image classification problem, where each image is rated on a scale of 0 to 4, representing the progression of the disease. So due to resource constraints, we only utilize the training directory, which has over 35,000 images and labels. We resize the images to 512 by 512 and then perform stratified splitting. Upon performing EDA, we also found that the dataset has severe class imbalance, so later on we should consider using metrics like Cohen's kappa and F1 score rather than accuracy. For our baseline strategy, we primarily decide to leverage TIM library and use models like ResNet50 in VIT, along with a very simple trading pipeline shown here. So we use very simple data augmentations. There is no real data imbalance handling yet at this stage, and then we evaluate the model using the quadratic weighted Covens kappa score, in short, which is QWK score. So we can think of this metric as if it will penalize the model more if its predicted class is further from its ground truth class. For example, if the class is 4 and we predicted 2, then it penalizes the model quadratically rather than if it predicted 3 instead. So below are the baseline results. We can see that judging from the table, the ResNet50 pre-trained model stands out as the most balanced model, even when trained with less epochs and less time. We can see that it achieved the highest QWK score. While VIT has a higher theoretical capacity, it likely requires more data, more aggressive hyperparameter tuning, or training for more epochs if it wants to surpass a well-tuned ResNet50. In terms of strategy for our extensions, first we decided to keep track of other metrics like F1 score and recall from now on, since they are more clinically relevant, along with core experiments like improved augmentations and class imbalance handling, exploiting the ordinal structure of diabetic retinopathy. Then we apply the best configurations to VIT. For our improved augmentations and class imbalance handling, first we found that our original augmentations were very simple and that they can potentially be harmful. For example, the reasonings that we show here. So we go for a more controlled augmentation pipeline. First, we use more controlled geometric and affine transformations, and then we have and then we add photometric enhancement like contrast enhancement and color jitter, and then we limit the distortions caused by rotations and Gaussian blurring. So in terms of class imbalance mitigation, we incorporate class-weighted cross-entropy loss, where the weights are inversely proportional to the square roots of class occurrence. So below are the results. You can see here that the model with the improved strategy performs slightly better in terms of QWK score, but the star are the recall scores, in which we can see that we see on the right that the model performs slightly better on the rare classes like 1, 3, and 4. So we will be using this configuration for the next experiments. Next, we would like to take advantage of the ordinal nature of the dataset, as in the classes themselves have a relationship with one another, each class being more severe than the last. So this implies that the distinction between predictions matter. So for this, we apply a combined loss formulation that uses weighted cross-entropy loss and ordinal regression loss, which is essentially just the mean squared error loss between predicted class and ground truth label. The formula for the total loss is given below. The lambda value is there to control the impact of the ordinal regression on the total loss. So we specifically evaluate the impacts of incorporating the ordinal regression using 3 different weighting factors, 0.3, 0.7, and 0.5. So below are the results of the experiments. You can see that the model trained with lambda 0.5 or a balanced loss function between ordinal and cross entropy far outperforms the other models in terms of QWK score, and it also has the most balanced per class recall score. Next, we revisit the VIT architecture, but now we train using the best and optimal training configurations thus far. So the results are shown below, and even though the VIT achieves slightly lower QWK score than the ResNet50 one, we can observe that all other metrics outperforms the ResNet50 variants. And furthermore, it also generally has a higher recall score for the rarest and more severe classes like class 4 and 3. And so for our conclusion, the VIT model with lambda equals 0.5 is selected as our best model, as it provides the best overall balance between highest F1 score, best recall score, and it also has a strong performance on moderate and severe DR classes. And also, while ResNet50 achieves slightly better ordinal consistency, VIT demonstrates a superior generalization and class balance overall. Additionally, our experiments prove that our extended strategies were consistently effective when applied on the diabetic retinopathy dataset.
Now I will present the multimodal classification test. Our goal is to classify the food into 10 classes using both the image and the pair tile text. For this test, we use the UPMC Food 101 subset with the pre-trained ClipVit B32 as the backbone, and we compare the zero-shot clip with the few-shot tip adapter. So UPMC 101 is the multi-module food dataset with 100,000 image text pair, where each sample contains an image, its text description, and the food label. And we use the 10 class subset so that the experiments stay manageable. For EDA, we found that the subset is clean and balanced, with no missing text or missing image, and the tile text is short, around 8 words on average. The train and test image distribution is also very similar. So here you can see the class count is quite balanced, and the tile length distribution is also quite similar too. This is for the image width, height, and aspect ratio distribution of the train and test subset. And for the outlier detection, there is a very small percentage of unusual in tile length and the aspect ratio. So overall, the subset is suitable for evaluating multimodal classification. For implementation, we use a custom multimodal dataset, and the data load the image are processed with the clip dataset. Text is tokenized with the clip tokenizer, and we test 1, 4, 8, and 16 shot per class for the few shot setting. And for the clip architecture, the key idea here is that it maps both the image and text into the same embedding space, which allows us to combine both modality naturally for prediction. In the zero-shot clip, we encode the image and tile text, then fuse them with weight 0.6 for image and 0.4 for text. And for classification, we create the prompt template for each class and compare the fuse feature with the class text prototype. For few-shot learning, we use the tip adapter. It keeps the pre-trained clip and we use a cache from the small label support set, then use similarity to those support examples so that it can refine the final class score. Here, alpha control the cache contribution and beta control the similarity sharpness. So for comparison, the zero-shot clip is already very strong with 97.22% accuracy. With the few shot tip adapter improved it slightly, with the best result is the 16 shot with 97.62% in both accuracy and micro F1. We also implement some extension. The first is calibration, where we can see that the few shot module is slightly more accurate, but also slightly more overconfident, which is shown by the ECE increase from 0.0102 in zero shot to 0.0174 in the 16 shot. Next is the modality ablation, uh, where we only use image versus only use text, and when we use the fuse feature. And the text only is stronger than the image only on this subset, but the fuse representation is clearly the best, so that we see that combining both the image and text give the strongest overall performance. And finally, in the interpretability example, uh, we can see that this image is true prediction is waffle, and by removing the word apple in the text, it caused a large confidence drop, and flip prediction toward the correct class is waffle. Also, occluding the top apple topping region also reduced the confidence, so that it showed that the module relies on both textual and visual cue, which can impact the final prediction. So overall, clip already performed very well in zero shot, and tip adapter give a small few shot improvement. Wow, and also the multimodal fusion is the strongest setting. So this is the end of our prediction of our presentation. Thank you for your listening.